So, welcome to the live interactive session of the third week of the course Engineering Mechanics. So, as I mentioned in the previous sessions, I will be solving some demo problems which will be related to your assignment problems for the corresponding week. So, I expect everyone to come here after watching the video for the corresponding week. And also, you might have already received the assignments for the third week. I hope you might have tried doing that. So if you have any doubts regarding the assignments or especially the content of that particular week or the previous weeks, so you can ask me either in between or at the end. So I will be giving extra time for you to ask these doubts. So basically I will go through some demo problems. So right now for the week 3 contents. So we'll start now. So I have the first problem. Find the magnitude of the bending moment in a cantilever beam shown in figure 1 at a distance of 0.5 meter from the fixed end. So options are given: 1.5 Newton meter, 1 Newton meter, 2.5 Newton meter and 4 Newton meter. So I hope the question is clear to everyone. So please try doing this yourself, and I'll give some time for you to try it out. So I want this to be an interactive kind of session. So if you find the answer, you can just let me know in the chat box. So after that, I will start explaining myself how you can approach this. So you can try this now. So basically this is a fixed end. I am marking that as let's say the end A, and let's say the other free end is B, and remember there is a force at the free end B, 5 Newton. So this is only Newton. Okay, it's not Newton meter, it's just a force. And at 0.75 meter from the fixed end, that is point C, there is a 1 Newton meter moment is acting. So you just need to evaluate the moment at a distance of 0.5 meter from the fixed end. So that will be exactly somewhere in the middle. Let's say this is the point which is D, which is actually 0.5 meter from the fixed end. So you just need to evaluate the moment at that point, just the magnitude. So anyone find the answer? So if you find the answer, you can put in the chat box. So this is basically a simple question. So anyway, I will try explain how to do this. So meanwhile, if someone find the answer, you can put in the chat box. Okay, we will review the answer. So basically we have to find the moment at the point which is 0.5 meter from the fixed end, which I denoted here as D. So moment at the location D is what we needed. So we can take moment about A. So doesn't matter from wherever we take the moment, it will be same. So let's find moment about A. We have to evaluate. So that is for the equilibrium thing. So we have to actually evaluate the moment at the location D. So we have to evaluate the moment at D. So consider a section, let's say XX, which is passing through the point D. So we have to either take the moment caused by all the forces and torques on the right side, or we can consider the moment which is caused by all the forces on and the torques on the left side of the section XX, which is passing through the point D. Just that they will be equal and opposite in sign, because we only want the magnitude, doesn't matter. So basically we are evaluating the bending moment at the section XX, which is passing through the point D. So as I mentioned earlier, so you can either choose the left side or the right side. So here I am going to choose the right side of the section XX, all the forces and the torques on the right hand side, because all of them we know. Just the 5 Newton is acting at B, and at C there is 1 Newton meter is acting. That's the only force and torque acting on the right hand side. But on the left hand side, you can still choose it, but it's a little more involved. So you have to first identify what are the forces and torques present in the left side. Unlike the right side, which is a free end, left side is actually a fixed end. So you will have support reactions. So in the first view you will see there is no forces or torques, but actually at this support you will have a support reaction, a vertical reaction RA, and there won't be any horizontal reaction. But generally you will consider it, because it's a fixed end, you can have horizontal reaction as well. But because this is just the vertical load, if you see the entire system at the end B, there is only a 5 Newton acting vertically downward. So there won't be any there is actually no any horizontal force acting on the system. So there won't be any horizontal reaction at the support A. But if you want, you can consider as a general case there is a horizontal reaction, let's say HA, and you will later find that HA will be 0. So basically there is no horizontal reaction. You have to apply the equilibrium conditions that we learned in the last 2 sessions. And one more reaction will be present at the end A, which is reaction to the moment, because there is at the location C there is 1 Newton meter torque is acting. So to balance that, there will be, so which is actually acting at C, it is acting in the counterclockwise direction. So at A there will be a clockwise direction moment let's say MR is acting. It's a resisting moment acting at the location A. So you can evaluate them using the basic criteria: sigma Fx equal to 0, sigma Fy equal to 0. That's what I mentioned earlier, which is not needed here because there is no any vertical forces acting, and sigma M equal to 0 about any point. Using that you can evaluate RA and MR at the location A. Now so now you have, if you consider the section XX, on the left side you have all the forces which are known, which is RA and MR. Once you do that, so you can use either of them, you can use those reaction, this reaction and the reaction moment on the left hand side to evaluate what is the bending moment at the section XX, which is passing through the point D. Or the other way, you can consider right hand side only. You don't need to solve the equilibrium equations at all. You can just consider right hand side, where you already know what are the forces involved. 5 Newton and 1 Newton meter is acting. So you can just choose the right hand side. So I will choose the right hand side, and consider right side of section XX. And now you know all the forces and torques or moments acting on the right hand side. There is a 5 Newton acting at B and 1 Newton meter acting at C. So let me consider the clockwise moments as negative and anti-clockwise moment as positive. So then moment at the location D, which is basically at the right, we can consider all the forces and torques on the right side of the section XX. So the 5 Newton is causing a moment which is actually from the XX section, it is 0.5 meter, right? Because which is the section XX exactly at the middle of the beam, which is of 1 meter. So from D to B you will have 0.5 meter, and this is causing a clockwise moment, so I am taking this negative sign. Then we are going to add the another moment on the right hand side, which is at the location C, which is 1 Newton meter. So just 1. So that's all. No other moments on the right hand side and no other forces on the right hand side. So if there is a force, the force multiplied with the moment arm from the location D to that particular force will cause a moment. That we already accounted. At location B we had a force and we multiplied with its moment arm, which is 0.5 meter. And at location C, which is actually 0.25 meter from the location X or location D, but already the moment is given. So at the location C, moment is acting, not a force, so we don't need a moment arm extra. We can just add the moment on the right hand side. So what we will find is that it's minus 2.5 plus 1 is minus 1.5 Newton meter. So it's basically moment at D is 1.5 Newton meter. Now we'll see what is the convention means. Negative is actually clockwise, so we can say it's clockwise moment if you consider the right hand side section. If you are considering the left hand side, we will find that the moment at location D will be minus 1.5 Newton meter or 1.5 Newton meter counterclockwise direction. Basically it's an internal location, right, inside a beam. So the net moment, if you evaluate from the left side and right side, should be equal and opposite, so that the internal moment will be balanced at location D and it will be in internally in equilibrium. So but here it is just asked the magnitude, so we only need 1.5 Newton meter. So option A is the answer. So is this clear? Any question in this? Good. So then we will move to the next problem. So calculate the supporting force and moment at the fixed end of the cantilever beam shown in the figure 2. So we have a cantilever beam here. So the fixed end, as mentioned earlier, we have A as a fixed end, and here we have a uniformly varying load of maximum intensity of 150 Newton per meter, and it is distributed over a length of 0.5 meter from the fixed end as shown in the figure. So we just need to evaluate the supporting force. So basically the reaction at A, vertical reaction at A. So because A is a fixed end, so you can have both vertical reaction and horizontal reaction. As mentioned earlier, here there won't be any horizontal reaction, but as a general purpose we will consider that also. Then you can have a supporting moment also. So let's say M at A is a reaction moment at the location A. So you are expected to evaluate the reaction as well as the moment. So I'll give you some time for you to try this out. It's also pretty simple, basic concept only. So if you find the answer, you can put in chat box. Okay. So anyone got answer? Either the support reaction force or the support moment. So I expect you guys are trying this, not waiting for me to solve this. So for the people who joined late, so I will be trying some demo problems related to the week 3 content of the session. So I hope already you have watched the lecture videos and have some basic idea of what is today's content and basic problem solving idea. So here is a demo problem. So we are expected to evaluate the horizontal or the net reaction at the fixed end A of this particular cantilever beam, which is loaded with a uniformly varying load. So anyone got the answer? Okay, so I will start explaining. So if anyone find the answer, you can put in the chat box. So we will basically use the so this is equilibrium equations for a planar system. The net horizontal force should be 0, net vertical force should be 0, and net moment about any point should be 0. So if we use the horizontal reaction equation, so there is no horizontal forces acting in the system. So we can say HA, which is balanced with 0 itself. So basically saying that HA is 0. And vertical forces, so we have VA acting upward at the location A, and the UVL is acting downward. So minus the net force which is due to the UVL. So it's a triangular distribution. You can just take the area under the triangular load distribution. So it's basically half into, so the UVL is basically equivalent to a force. Let me draw it with a different color. So I can replace the entire UVL, excuse me, with this kind of a force whose intensity should be, or its value should be, half into base is actually 0.5. Okay, so we'll check whether it is correct or not. Somebody has commented. Okay, so what I was saying is, So we have to balance VA with the intensity due to UVL. So it's the intensity of UVL is half into base, which is 0.5 meter, through which it is actually distributed, and the maximum height it has is 150 meters. So it's 150 by 4. That's its intensity. So which is 37.5. So VA should be actually balanced by this 37.5 Newton. So we can say VA should be actually 37.5 Newton. So it's not 100, it's 37.5. I hope that is clear. Anyone has any question here? It is not 100, I think it's 37.5 only. Okay, so then we'll move to the moment equation then to evaluate the reaction moment. So now let's say moment about A we are going to evaluate. So this should be 0. So moment about any point we can evaluate. Let us consider point A. So at point A there is horizontal force and vertical force is there, but horizontal force anyway is 0, HA is 0, that is not going to cause any moment. VA is there, VA is 37.5 Newton, but it is passing through the point A, so there is no momentum is 0. So VA is also not going to create any moment, but there is a moment, reaction moment MA is acting, which is acting counterclockwise direction. So yes, that will come to actually the intensity of UVL is actually acting 2 by not 2 by 3rd, it's actually acting 1 by 3rd from the fixed end. So I will explain that. It should pass through the center of the area. Okay, that's the basic concept. So first we will write the moment equation, so which is so let me not confuse you with the notation. So here I am writing the net moment about point A. Okay, somebody raised a hand. You can ask question if you have any. Okay, I think that's a mistake. So in case if you have a question, please ask, or you can type in the chat box. Okay. So I was saying about the notation. So MA I am here writing basically for the moment about point A, and I will use MR to represent the reaction moment at the location A. So even though the forces HA and VA are not causing moment about point A, because their forces passing through the point A, they don't have momentum, so they are not causing any moments. But the reaction moment MR is passing through the point A. It's not actually passing through, it is actually acting on the point A, so it will be still present there. It does not require a momentum to be exist. It's a moment, it's not a force. So MR should be there. It's acting counterclockwise, so we'll take the counterclockwise to be positive, just the convention. Okay, and now it should be and there is another moment which is caused by the UVL, and from the figure we can say that, let's say it is acting at a distance x from the fixed end A. Okay, again some hand raise. So if there is a question, please go ahead. Are you not able to unmute yourself and ask the question? So you can type in the chat box. In that case, I will answer that. So what I was saying is MR is acting there, and the resultant force due to UVL, let us call that as F. So we have evaluated that is 37.5 Newton only. So that F is actually supposed to act at a distance x from the fixed end A. We will see what the x is, which is causing a clockwise moment. So x times F, they should be balanced to 0. So we can say the moment reaction at the support A should be x times F. Now F we already evaluated, which is 37.5 Newton. But what is x? So someone has pointed out it should be 2/3 from, I don't know whether he meant it from the fixed end A. It shouldn't be 2/3 from the fixed end A. It will be 1/3. Okay. So basically it should pass through the centroid of the load diagram. So you can, it's basically, if I say this is a centroidal location, it will be 1/3 of the entire base, and this will be 2/3. So now if you measure the distance from the fixed end, you have to measure it from the fixed end only in this particular case, because we are taking the moment about the fixed end. So it should be 1/3 of the base. So that x is basically good. So x is basically 1/3 of the base, which is 0.5, times the force, which is 37.5. So let me evaluate it. It is 6.25 Newton meter. So that's a reaction moment. So we have evaluated the reaction force to be 37.5 and the moment to be 6.25 Newton meter. So basically the reaction force is the resultant of the horizontal and vertical force. Just that we don't have any horizontal reaction, it will be just the vertical reaction, be 37.5. So I hope that is clear. Any doubt in this section, in this question? So if nothing, we will move to the next problem. So which of the following statements are always true? One or more options may be correct. So we have 5 options. Sorry, 5. In principle, actually 4 options are there. So we have to check which of them are correct and which of them are not. So because there is nothing to analytically evaluate, I will just going through each of them and I will ask your opinion about it, and I will explain whether it is correct or not. So a point load causes a finite jump in the shear force diagram at the corresponding location. Is this true or false? What do you think? Yeah. So someone has pointed it is true. Any other opinion? So it's actually true. So now we'll see why it is true. So basically a point load, let's say we have a beam and we had a point load acting at some particular location. Then the shear force diagram, okay, someone has pointed, okay, second may also be correct. Let us see. I'll just mark that. So the point load is basically causing the shear force diagram to shift by that much of amount of the force which is acting at that particular location. So that is anyway true. Basically the point load at that location is contributing to the shear force which is acting on that particular location we are evaluating. Now we'll come to the second point. A point load causes a discontinuity in the bending moment diagram at the corresponding location. So somebody was thinking it is correct. Is this correct? So remember, the slope of the bending moment diagram is the shear force, or the slope of the bending moment gives the shear force, and slope of the shear force gives the loading. So if we have so if we start with a loading distribution, some kind of loading, let's say an UDL is acting, its corresponding shear force diagram will be, so this is loading diagram. Now if you see the shear force diagram, so UDL is like a constant distribution, right? So it should be a linearly increasing distribution. Of course we need support reactions as well. So let us consider a end which is, this is basically, okay, let us simply consider a cantilever beam. So it will have an UDL here, so it will have a reaction force acting here. So if we now draw the shear force diagram, it should increase like this and then should go to 0, and the bending moment diagram should be like this. So it will be, the shear force will be linearly increasing, and the bending moment diagram will be quadratic in nature. So this is, we will see detailed discussion on this kind of problem. Just for the moment I am just explaining. Let's say if there is a point force acting at this particular location in this particular loading, we are expected to have a shift in the shear force diagram like this, but that will not change anything in the bending moment diagram, because you can see what I was saying is, so the slope of the bending moment diagram, or the bending moment, will give the shear force, and slope of the shear force will give the loading, or in other ways the integral under the shear force diagram should give the moment, and integral under the loading diagram will give the shear force. So if you consider a point load, that will cause a change in the so basically this shear force is shifting, this particular force acting at this location is shifting the shear force diagram by that much of amount, or displacing the shear force diagram a little bit, but that is not changing its slope, only it's shifting it. So it's like you cut that much of part and moving it down or up, depending on how the force is acting. So I drawn here a force which is acting downward, a point force P acting at this location, which is going to shift the shear force diagram at that particular location by that much of amount. And after that, in any other section if you consider, it will be the same shifting. Everywhere the shift will be same. So that's only causing the shear force diagram to shift that much amount, but it's not changing its slope. You can see the slope at this location is same as this location. It's continuing to be the same slope. So the slope of the shear force diagram is the loading, right? And now if we evaluate the area which is of the shear force diagram, which is going to give the bending moment diagram, right? So let's say until this particular location you have evaluated the area of the shear force diagram, which is going to give the corresponding moment until this particular location. And now the point load P is acting, and your shear force diagram has changed as I have drawn here. And now if you take another section here, and the extra area you are getting added is here. The extra area you are getting added to the previous shear force from the previous shear force diagram. Now it is changed a little bit because of the forcing, the extra forcing. So the extra force, that the extra moment because of that is the area under this region, which is I have marked as the green color. And now if you think, that's a finite quantity, even though the force which is caused this kind of a shift in the shear force diagram, which is a point load, which is a sudden variation. You can think the loading was UDL, and suddenly there is, or if you actually draw the loading, it was a uniformly distributed load, so which was something like a constant load until this, and suddenly there is a point load acting, which is causing the load to shift like this, a point load shift, and then again it remains a constant. But what happens in the what happens due to this sudden loading in the bending moment, in the shear force diagram, is it's extra adding this much of area, a slight area, and this is not a, so if you evaluate the area under the shear force diagram, give me a second. Yeah, so if you evaluate the area under this shear force diagram, you are going to get the bending moment. So the extra area that I marked here in the green color, in the limit of the location which is close to that particular point, excuse me, you will find that area is negligibly small, even though it is caused by a point load. So what I want to say is that this is going to not going to alter the bending moment diagram in a not with a sudden jump, but with a sudden slope change. So I hope that is, I don't know whether that makes sense to you. If it is not clear, you can tell me, so I will try to explain it again. Am I audible? Okay, good. So I will explain again. I will try to explain in a different way. Probably that will be better. So you agree with the first point, that is a point load causes a jump in the shear force diagram. So that's like, let's say point force is acting at particular location, and you have a shear force I will represent as V. At some particular location, a point load is acting. Because of that, sudden discontinuity is going to happen in the shear force diagram. So if I just draw the shear force diagram, so this is a shear force diagram. So I had some kind of a distribution, and suddenly because of a point load I had a sudden discontinuity in the shear force diagram, and then again it is continuing in the same fashion as it was previous. It was previously supposed to be continue like this without action of a point load, but because the point load acted at this particular location, the shear force diagram is shifted like this. Just a sudden jump happened at that particular location. Now what will be the effect of the corresponding bending moment? Because the second point also says it's like the continuation of the first point. You have the same point load acting at a particular location. In the first point it says that it's causing a jump in the shear force diagram. Second point says that it's causing a discontinuity in the bending moment diagram also. We have to just verify whether it is correct or not. Now if you try to plot the corresponding bending moment diagram, so it will be like quadratic like this, because basically at every location, so we are measuring the x from this right to left. Okay, so let's say we take a section xx and try to evaluate the area under this, and we will call that as the bending moment. So I hope that concept already you might have understood from the videos, lecture videos. So we will mark that as the bending moment at the location x, and we will plot that in the bending moment diagram following the x direction. So let's say this is the bending moment at the location x, the area under that particular marked region. So that will be this value we are plotting here. So that we will repeat gradually. We will evaluate, shift the section xx each time to a different x location and try to evaluate it, and finally when we reach here at the location where the point load acting, until that everything is straightforward. You will just evaluate the bending moment until this location. So we will get some quadratic profile if the the shear force was linear, just the integral. And now what will happen at this particular location where the point load acting, where we have a discontinuity or jump in the shear force diagram. Basically on the right hand side of that particular location where the point load acting, we will find that it's just the area until this region, which I marked as green color. And in the right hand side, I mean it's like a limiting process just below and after the point loading location. So if you think it's in a limiting case, just below the just before the point load acting, in the shear force diagram it had some value of shear force. Just after the point load, it has an extra point load added value of shear force. So that's why there is a discontinuity in the shear force diagram or sudden jump in the shear force diagram. But if we move to the bending moment diagram, basically we are evaluating the area under the shear force diagram until that particular location. Now if you think a point just before the location where the point load is acting, let's say let us mark this is the location. Now just the area, if you evaluate, it will be like quadratic profile as I have drawn here. Now if we consider a point which is limitingly after, in the limiting sense, after the point load, somewhere here, I mean it should be very close to that particular location point where the load is actually acting. And now if we ask what is the bending moment, we have to basically evaluate this area, the marked as green color. Now in a limiting sense, if you do this process, basically saying that this point is very close to the location where the load P is acting, you will find that the extra area added because of the point load is actually 0, because it's like a the point load, right? So the load is actually acting at a point location, so the extra area will be the P times the distance at which the load is acting, which is supposed to be a point. So extra area added is 0. But if you move a little bit further, you will see there is an extra area gradually getting added, not suddenly added. That's the point I want to make. This area, this is extra area, right, because of the point load, and this is actually gradually getting added. So what does implies that it's not a sudden variation that is going to happen in the bending moment diagram. So it's not like the bending moment has a sudden jump like this and then it will continue like this. There will be a sudden variation in the slope, not in the value of the bending moment. So let's say until now the bending moment was something like this. So after this point, once the point load is acted, its slope will change and it will continue to be a piecewisely continuous function. It won't be a discontinuous function. That's what I wanted to say. I hope that is clear. Okay, I drawn this wrongly, so it will just continue something like this. It's drawn wrong, but I just want to convey the point that only the slope will be discontinuous, because the slope of the bending moment diagram is supposed to be the shear force diagram. So we already know there should be a discontinuity in the shear force. That means the slope of the bending moment should be discontinuous, not the bending moment itself. It is discontinuous because of a point load. Is this clear? So in simple words, I think I would say, just if you look at the equations. Okay, good. So in the simple words, you can just think of these equations. So first of all, we told there is a point loading, so that is causing a discontinuity in the shear force. So if the discontinuity is present in the shear force, we can say the slope of the bending moment has a discontinuity. That doesn't mean bending moment is discontinuous, just that its slope is discontinuous. Bending moment will be still continuous due to a point load. So according to that, the option 2 is actually not correct. So, but if you see the third option, a point load causes sudden change in the slope of the shear force diagram. It's like the opposite condition, and you know that won't happen. A point load always causes value of the shear force to be changed, or the shear force diagram will have a jump, but its slope will be preserved. Okay, because the slope of the bending moment diagram, the slope of the shear force diagram supposed to give the loading, intensity of the loading at that location. So that says the option 3 also not correct. Now if you see the option 4, a point load causes sudden change in the slope of the bending moment diagram at the corresponding location. So basically, it's actually, if you see, it's actually equivalent to the first point itself, because the slope of the bending moment is going to give the shear force. So it's basically saying the first point itself. A point load causes a sudden change or a jump, finite jump in the shear force diagram at that location. So because the fourth point is equivalent to the first point, they are same and they are correct. So is this any question in this particular section? So just you need to remember this. A point load causes a jump in the shear force diagram, but that will not affect the bending moment diagram. I mean, there won't be a sudden jump, there will be a slope change. But a point moment will not affect the shear force diagram. It will affect the bending moment diagram. There will be a sudden change in the bending moment diagram, a point moment. So these are the two things you need to remember. We will use this concept in the coming problems where we will try to draw the shear force diagram and bending moment diagram. Okay, so I hope no questions here. So if it is not clear, you can ask again. Okay, so we'll move to the next problem. So we have a simply supported beam. So we had to just evaluate the support reaction at the roller. So let's call this end as A and this end as B. So we just need to evaluate the reaction at B. So I'll give you 1 minute to solve this. Pretty simple. We have a follow-up question of the same problem. We will see that next. But first you have to evaluate the reaction at B. So you can try. So anyone found the answer? So we'll have a reaction at A and reaction at B, and there's no fixed joint, so only support reaction forces will be there. And because all the loadings are vertical, there won't be any horizontal reaction. So there can be a horizontal reaction at the pinned joint A, but because there is no other horizontal forces, there won't be any horizontal reaction. I guess by this time you have clear idea of how to avoid these kind of unwanted reaction forces. So we'll just solve the equilibrium equation. So RA plus RB, the vertical reactions, should be balanced by the net down forces acting on system. So 100 Newton acting at the free end plus the distributed load. So basically the 300 Newton which is here, which is a uniformly distributed load, and there is an uniformly varying load acting here. So each of them we can replace by its equivalent version of point load. So if I say this, its equivalent is F1 and its equivalent is F2. So F1 should be the area under this region, right? So it's actually base 4 times height 300, so it should be 1200 Newton, and it should pass through the centroid of this area, which is, you can say, passing 2 meter from this end and 2 meter from that end. Okay, and now if we consider the uniformly varying load, the area under this particular triangle is what we needed for the loading, so which is F2, which is half times 4 times 300, so which is basically 600 Newton, and which should pass through the centroid of the area, which in this diagram you can see 2 by third into 4 meter from the end A and 1 by third from the other end, but that doesn't matter because we are going to take a measurement either from point A or point B. So I think I will take from the end A. So just need 2 by third of the 4 meter, which is 8 by 3 meter. So we'll come to that when we take the moment equation. So if you just consider the horizontal vertical reaction balance, Ra plus Rb is upward forces, should be balanced by all the downward forces. So which is 100 Newton plus F1 plus F2, the equivalent of the distributed loads. So Ra plus Rb should be equal to 100 plus 600 plus 1200, which is 1900. And now if we take the moment about A and say it is should be 0 for equilibrium. So the RA reaction is passing through the point A, which does not going to cause moment about point A. RB, which is actually 4 plus 4 plus 2, 10 meter away from the point A, which is causing an anti-clockwise moment, and 100 Newton is 12 meter from the end A, so which is causing a clockwise moment. And again F1 and F2, they are also causing moment, clockwise moment. So F1, which is 1200 Newton, which is actually 4 plus 2, so which is actually 6 meter from the end A. So 1200 into 6. Then 600 Newton, which is 2 by third of the 4 meter, which is 8 by 3 meter from the pinned end A. So this should be balanced to 0. If you solve, you will find RB. Let me evaluate it. So 100 into 12 plus 1200 into 6 plus 600 into 8 by 3 is 10,000 divided by 10 is going to give RBS 1000 Newton. And from the first equation you can say RA should be 900 Newton. So here it is just asked to evaluate the reaction at B, so which is 1000 Newton. So option D is the correct answer. So this is nothing to do with there is nothing much from the week 3 session. It's all 1 and 2. So I hope you guys can do this faster. Nothing complicated happening here. Just that you have distributed loads here. You just need to understand how you evaluate the effective loading and through where it passes. So now if you move to the follow-up question, for the same beam as shown in the previous question, calculate the maximum bending moment and its corresponding location on the beam as measured from the pinned joint from A. So we measure from the end A. We just need to evaluate where the maximum bending moment occurs. So you have options given here. So where and what is the maximum value of bending moment? So it will take a while. You have to basically plot the shear force diagram, bending moment diagram. So that's a actual procedure. There can be shortcuts. So because we are learning the course from the basics, so you will first draw the shear force diagram, then the bending moment diagram, then you will identify where can the maximum bending moment come. So it corresponds to the maximum bending moment is an extrema of the bending moment. So its slope, which is a shear force, should be 0 at that particular location. So you can easily identify that location and the value of the bending moment, then you can evaluate at that particular location. So you can try this. I will give some time, then I will explain how to do this. Okay. So I expect you guys are trying this out. So if you don't want yourself to try, you can just tell me. I will barely explain it. So I am giving time for you to try this out um, before me being solving it directly. Okay, so I think I was hiding the question. So this is the beam. So for this beam, you have to draw the shear force diagram, then draw the bending moment diagram, and identify where is the maximum bending moment is occurring and what is its maximum value. So anyway, I will start explaining. So if in case if somebody find the answer, you can put in the chat box. So we'll start with the loading diagram. So loading diagram is nothing but what is given in there. Just that we'll additionally have the reaction forces added to it. So if you see, basically you have a beam, and at the right end there is a 100 Newton is acting here, and at the location B there is RB is acting, which is 1000 Newton. Then at A we have 900 Newton acting. Then there is an UDL which is acting in this area, and then there is an UVL acting in this area. So which are equivalently replaced by F1 and F2 earlier. But now we cannot do that because we are going to consider each and every section and evaluate its shear force and bending moment. So we'll start now by plotting the shear force diagram. Before that, let me mark the distances. So this entire length is supposed to be 12 meter. So in the question it is asked to find the distance as measured from the pinned joint, which is supposed to be A. So I prefer to measure from the other direction, just for plotting the shear force and bending moment diagram. then we'll find the location, and then we write the location in terms of if we measure it from the other end. So you can choose to measure from the end A, but I think we can, it doesn't matter from where you measure, you should get the same result. Just that the final answer is asked to be measured, the location where the maximum bending moment occurs should be represented as it is measured from the end A. For plotting the shear force diagram and bending moment diagram, it doesn't matter from where you measure. Just that you will get like a sine reverse the result, that's all. So what I was saying is I will measure from this end. So this is the x direction I am measuring, and or I would say like this. So from this end I am measuring x in this particular direction. So now the shear force diagram. So when x is 0, we are at this end and we have a shear force of 100 Newton acting downward. So this will be 100 Newton like this. Then there is no other forces acting on the system. So if we now consider a section, so at this particular location, let's say xx, you have to consider either right or left of that particular section xx and add all the forces on that particular side. So I am only considering the right hand side, and you can see on the right hand side only 100 Newton is acting. So the shear force at xx will be 100 Newton downwards. So the 100 Newton continue to be the shear force at this location as well, xx. Now if I move the xx to another location which is just before this 1000 Newton, excuse me, you will still see that there is no other force acting on the right hand side, so that the support or the shear force just before the 1000 Newton is still continue to be 100 Newton. Okay, I will do one thing. I will just change the scale of the 100 Newton because I have to draw, and I will draw it again. I am just changing its scale so that the lines will look somewhat realistic, even according to the magnitude. So let me start again. So this is a shear force diagram. So we will start from this end, and I said 100 Newton is acting here, and if we consider any section, so let me mark the points here. So this point was A, this point was B, this was C. Let me mark this as D and E. So now let me repeat again. So if we consider the point C, which is this end, you have a shear force of 100 Newton acting downward, that I have drawn here. Now if we consider a section xx, which is in between B and C, which is at a distance x from the end C, just consider the right hand side. As I mentioned earlier, you can either consider the left hand side as well of the section xx, but here I am simply choosing only the right hand side, just a convention. You have to follow a particular convention. So I am taking a section xx and only considering the right hand side of the section xx and adding all the forces on the right hand side of the section xx. Now if the section xx is in between B and C, if you look at the right of the section, you will only see 100 Newton acting downward. As a result, you will have only 100 Newton as a shear force for any x which is in between B and C. So if I mark the point B here, until the point B, 100 Newton will be the shear force, will continue to be the shear force. Now if you cross the point B and came left of the B, basically x is, now our section xx is somewhere here. between B and D. Now if you see the right hand side of the new X location, you have 100 Newton downwards and 1000 Newton upward. So the resultant of 900 Newton upward is there. So the sudden change from 100 Newton to 900 Newton in the negative to positive value is happening at the location B. So what you will see is that the shear force is changing like this and continue to be 900 Newton after B until D. So until the location D, there is nothing else is changing, no other force is acting. From D onwards, from the point D onwards, there is again vertical load, which is not a point load. So as I mentioned earlier, the point load is now, you can see, causing a discontinuity in the shear force diagram. We will see equivalent bending moment diagram, but you can see the point load is making sudden changes in the shear force. For example, at location C, you can see it's changing from 0 to 100, 0 to minus 100. And at location B, it's changing from minus 100 to 1000, 900. So no questions until here, right? Any questions? So we have drawn until...
Hello sir, so the shear force, how did we calculate the shear force?
So that's what we are calculating now, the shear force diagram. So basically we are plotting the shear force diagram here. So is the loading diagram is clear, right? Basically we are actually plotting all the loads here. So you can see both the question and the loading diagram that I have drawn. So the externally acting loads UVL, UDL and the 100 Newton I am plotted here in the locations AE, ED and at the point C. Then you will have external support reactions at location A, which is 900 Newton, and at B 1000 Newton. Now once you have the loading diagram, you have to take so basically it's like you have some beam, you have some load acting, some kind of loading, you can have support reactions. So basically if you say that you have a particular location, this is a location D, let's say I call it as Q, a point Q. You want the shear force at that particular location Q. You think that there is a section which is passing through that XX, which is cutting the that beam into two pieces. Okay, so now the section is cutting this into two pieces. Now you can either consider all the forces. So what is shear force? Shear force is an internal force which is acting at this particular section. So this is a shear force which is acting at this particular force. So this is shear force at Q, this is shear force at the location Q. And they on the right hand side and left hand side, they will be equal and opposite, for it should be in equilibrium. So it's like you had compression and tension earlier, right? So if you consider there was a member here, there is an internal force, compression or tension, they will be equal and opposite in that member, and they will effectively add up to 0. The same happening here also. You have an internal force, but not a normal force. It's not acting normal to the member, but it's acting in a shearing manner. So they will be acting like this, equal and opposite forces at that particular section. Every section this is there. Every point in that beam, there is an internal force equal and opposite which is acting on it because of the external loading. For the beam or the member to be in equilibrium, they should be equal and opposite. And if you see on the right hand side, this entire shear force which is acting on this area should be caused by the external load acting, or should be balanced with the external load. So you can basically say that this shear force acting here is basically sum of the entire force acting on the right hand side. And in other words, you can say the shear force acting on the left hand side, which is also caused by the sum of all the forces acting on the left hand side, and they should be equal because they should be in this entire system structure is in equilibrium, so they should be equal and opposite. But shear force is basically an internal force, so you can either consider the right hand side of the section or the left hand side of the section and just add up vector sum of all the forces acting on either right or left of that particular point. Good. So here what we are doing is basically we are plotting a shear force diagram, how the shear force is distributed across the B. So we will start with some end which is at the location, so some point which is at C, which is at the right hand end of it. We can start from the left end also. It's better to start from some end, shouldn't start somewhere in the middle, because it's like you're gradually evaluating the shear force from one point to another point, because it's an area under the loading diagram, that is you are getting the shear force. So start from one of the end, start from end C. So we see that on the right hand side of the point C there is no forces, so the shear force should be 0. But on the left hand side of the point C in the loading diagram, you can see that there is suddenly 100 Newton acting. It's like a limiting process, point C and before and after, suddenly a load 100 is acting. So now if you take the point C, the shear force at the location C is suddenly changing from 0 to 100 in the downward direction. So that's what I have drawn here, 0 to 100, a sudden variation, shear loading. Then you consider another location in between B and C. Why I am saying any location between B and C is that there is no other loading in between B and C. At C there is a point load, and then between B and C there is no other load. So take any section between B and C, any general section. Let's say it is from X distance from the end C. Now if you want to evaluate the bending moment, the shear force at that particular location X, you have to basically add up all the forces acting either on the right or on the left. I am here choosing to the right. So if you see a general XX section which I have drawn between B and C, the right of which only have 100 Newton down. So that means any point between B and C will have a shear force value only 100 Newton. So I continue to have shear force 100 Newton until, basically it's a minus 100, it's acting downward between B and C. So that's why between B and C I only have this much area, 100 Newton. Then at B it changes, 1000 Newton acting upward. So now if I at point B, what will happen is 1000 Newton is added to the minus 100, totally making it 900 Newton in the upward direction. So now if you now take any point between D and B, in the loading diagram you can see a section XX is plotted between D and B. Now if you think any point between D and B, it's like some point here, you want to see what is the corresponding shear force at this location. You can think of the net force on the right hand side of that particular section. You have 1000 upward and 100 downward, resulting will be 900 upward. So a positive 900 Newton acting, and that will be true for any point XX or any section XX between B and D. So that's why I continue to be having 900 Newton in this entire region dB. Okay, so now from here we will have extra loading. So until now we only had point loads, but from D onwards we will have uniformly distributed load DE. in the entire area DE. So we should ideally have a location E here, until which we have a uniformly increasing load. So we have to consider a section between E and D. Let's call this as XX. And why I call this XX is that it is now measured X distance from the end C. Okay, so basically we have to if we consider the section XX, a general section XX, so I will redraw that particular region here of the beam. You have a load here and another load here, so this is 100 here, 1000 here, and then you have uniformly distributed load here, which is of intensity is 300 Newton per meter, but which is acting. So this is I am only drawing the right hand side of the section XX. So you either consider right or left. I am considering only right of the XX. So this is the distance X, and this distance is, so in question total distance is 4 meter. The UDL is distributed, but the UDL is starting from this much distance from the end C, which is 4 meter from the end C. But I am saying I am somewhere here, which is total of X distance from the end C. So only this much distance I am plotting there, which is X minus 4 units from the end C. So this distance is X minus 4 units. So is that clear? So if I say the section I am considering is X unit from the end C, the UDL is only distributed over X minus 4 units, because then the remaining 4 units, which is this and this, there is no UDL is present. Is that clear? So if that is clear, then what we supposed to do is that just add up the net force on the right hand side for any section XX, which is in between E and D, this area, to find the bending moment, the shear force. So bending moment also we will follow the same procedure, just that we have to add up the bending moment on the right hand side. Here we are plotting the shear force diagram only, so we will just do that. So consider any general section XX now in between E and D, which is a UDL, uniformly distributed loading region. The section X is from the end C at X distance units, but the UDL starting from D only, so that from D to XX location it will be only X minus 4 units, the base width of the UDL. So now if you consider the if you want to know what is the shear force at the location XX, we'll add up all the forces on the right hand side of this beam. Earlier we had 100 downward plus 1000 upward. Now extra load coming is this much area, which is an UDL, which is 300 Newton meter acting over X minus 4 units. So it can be simplified to 300 into X minus 4 plus 900. Okay, there is a mistake. 300 is actually acting downward, so it should have a negative sign. So we are considering the vertical shear force as positive, and upward shear force as positive and downward as negative. So 1000 is acting upward, 100 is acting downward, so that will resulting in a 900 upward. Then this 300 Newton meter UDL acting over X minus 4, so that product, the area under that, will cause 300 times X minus 4 Newton acting at somewhere here, I mean centroid of that area, which is x minus 4 by 2 units from the x end. But that doesn't matter now. That is only matter when we are going to evaluate the bending moment. In case of the resultant force, we don't need where it actually acted. So this is a shear force at that particular location, 900 minus 300 times x minus 4. So is that expression is clear? The 900 minus 300 into x minus 4. So if you didn't understand, please ask me, I will repeat it. So I hope this is clear. So if this is clear, then now we were actually evaluating the shear force at this particular x-axis location, right? So generally that is given by this expression. It's an equation for a straight line where x is measured from this end. When when the section x-axis is drawn at location, so this is valid in between E and D. Okay. So let's say at location D, we want to know what is the shear force diagram, the value of shear force. We can use this expression. What is the shear force at D, which is 900 minus 300 times x minus 4. Now x is for the location D measured from C, it is just 4 units, right? So this is a location D and this is a location E. Location D from the end C is only 4 units apart. So x is actually 4. So 4 minus 4 is 900 Newton. So that we already know because we were stopped until D only, right? So at location D the shear force is 900. We already have that. Now what is shear force at location E? So we will use the same expression again. 900 minus 300 times x minus 4. Now for the location E, what is x? So this is the location E, which is from C, it is actually 8 units apart, right? So x is actually 8. So it's 8 minus 4. Now we will find that it's a 900 minus 300 into 4, which is 1200. We'll have minus 300 Newton. So at E, we are saying the value of the shear force is minus 300 Newton. So it's somewhere here. So this is minus 300. Now in between E and D, any point, we can use this expression as to evaluate the shear force. But if you see it's just a linear expression, you can just draw a straight line connecting the points, both the points. It's supposed to be a straight line, and that will give you the shear force in this particular area. Any location, you can use this. So it's going from 900 to minus 300, passing through some point where shear force becomes 0. That is a point of relevance, because when the shear force is 0, shear force is basically slope of the bending moment. So that means bending moment becoming an extrema, either maxima or minima. In this particular case, we will see this is a location where the bending moment becoming maximum, and so this location is actually of importance. So if you want to find that particular location, let me call that as F. So we know the shear force should be 0. We can just solve this expression and find what is x value. So it's 900 minus 300 into x minus 4 is 0. You will find x minus 4 is 900 by 300, which is 3, or x is 7. So from the end C, if we measure F, which is at a location of 7 units, so where shear force is vanishing, correspondingly bending moment will be extreme. But we actually want this value measured from the end A, because in the question it is asked as measured from the pinned joint, which is A. So that's basically the total length minus total length of the beam. You can see AC, which is 4 plus 4 plus 2 plus 2, it's 12. So if you subtract from the 12, you will find the same length measured from the other end. So you can just say from measured from A, the point F is 12 minus 7 units apart, which is basically 5 meter. So where measured from the end A, 5 units apart, we will find the point F, where the shear force vanishing, correspondingly bending moment will be maximum. So now if you come back to options, you have two of the options which you have 5 meter location mark supposed to have a bending moment maximum. So now we have to find what is the bending moment maximum value to finalize which option is correct or not. So we can either continue plotting the shear force diagram, or we can skip and move forward to draw the bending moment diagram, or you can actually skip plotting the bending moment diagram also, because now you know the location F. You just need to evaluate the total bending moment at the location F. So in the interest of time, I will just skip that. I'll just evaluate the bending moment at the location F, which is the maximum bending moment. So MF or BMF, bending moment at the location F, I will be like I have plotted the shear force diagram, I will be following from the right side. So now I consider a section which is passing through the point F, which is somewhere in between E and D. I have to basically write the general expression for the, I can actually write the general expression for the bending moment at any location between E and D, considering it is at an x distance away from the point C. Or because we already know which point exactly we are trying to evaluate the bending moment, which is F, which is actually 7 units from the end C. You can directly evaluate it. We don't need to generally evaluate in terms of any x. We can say it's 7 units from the end C, which is location F. Only need to consider all the forces on the right of the point F and moment caused by that. So I am just going to do that. So we have anyway 100 Newton acting in the right end. So that is going to create a moment. So let me redraw the figure again, the loading diagram. So now we are considering the point F, and the section x-axis now passing through the point F. The loads acting are 100 Newton acting here at the end C, then 1000 Newton is acting at location B, then there is a UDL acting, which is supposed to act starting from D until E. So this is the E location, but because we are taking a section which is somewhere between E and D, we only will have that much of contribution on the right hand side of the UDL, which is from this much distance. So this total distance is we evaluated, which is 7 meter. The point F is actually 7 meter from the end C, and this distance BC is 2 meter and BD is also 2 meter. So this distance should be 7 minus 4, which is only 3 meter. So only 3 meter is contributed by the UDL. Now because we are taking the moments, we need the equivalent force due to this UDL. So which is basically 3 times, basically the base is 3 times 300 Newton meter, which is the intensity of this UDL. So 3 times 300, which is 900 Newton, which is acting through the center of this area, which is 1.5 meter from the end F. Now if we just evaluate the bending moment at F, consider all the moments either on the left or on the right of this particular section XX, which is passing through the point F. So now we are considering only right side. It will be equal and opposite in magnitude, that's all. So at point C, 100 Newton is acting, which is 7 units or 7 meter apart, causing a clockwise moment. So I am taking this negative. Just a convention. You only need magnitude and just say whether it is counterclockwise or clockwise. Then 1000 Newton, which is acting 5 units from the end F, or from the section XX. So it's 5, which is in the counterclockwise direction. Now the resultant of the UDL, which is 900 Newton, which is causing a clockwise moment. So 900 Newton, which is acting 1.5 meter from the end F. So these are the resultant moments caused by individual loadings. So we will just take the sum of this. So which will be, just give me a second, I will evaluate it. So we will get it is 2950 Newton meter. So this is the bending moment at the location F. So if we go back, option C, which has 29550 Newton meter, along with the location where it happened, which is 5 meter measured from the end A. So is that any question in this? Is this clear? So this is a little bigger question. So whatever asked in the question, we can just do this, like stopping the shear force diagram somewhere in the middle and only using the data from that much to evaluate the reaching the final solution. But I suggest you to complete the shear force diagram in the remaining area. So remember, now you have a UVL and varying load, which is a linear variation. So its integral, which will be quadratic, that is the shear force diagram. So if you draw, you will get something. I have the solution, I can draw that. So if we continue to plot the shear force diagram, it will be something like this, a quadratic profile. After the point E, and the corresponding bending moment diagram that I haven't plotted at all. So if you see, its shape should be, so from the free end, not at the free end, actually there is a loading, so it should increase something like this, then it should go like this and reaches a maximum and it changes slope and come to 0. Okay, there's a correction. Like this. So we have this point, which is B, and this is C, and the point where the maximum bending occurs is F, and yeah, this is point E and this is point A. So from E to A it will be a cubic polynomial. From E to D it will be a quadratic polynomial. And D to B it's linear. And okay. Sorry, yeah, this is not D. This is D. D to B it is again linear, and C to B also it is linear. So here it is cubic, here it is quadratic, and then here it is linear. So I hope you can try that yourself. So any doubts? So no doubts, we will stop here for today. We will meet next week. Thank you.